Okay, so now we move on to chapter 2 in M3, elastic strings and springs. Okay, so first in this chapter we learn about Hooke's law and equilibrium problems. Okay, so we can use Hooke's law to solve equilibrium problem involving elastic strings or springs. Okay, this question is introducing you about the concepts that we use when we work with elastic strings or springs. Okay, so what do you mean by elastic strings or springs? Basically, elastic strings or springs are the ones that extend when you stretch it, it pulls it. You can stretch it. Okay, so basically in M1, M2, the strings we used were not elastic. Okay, so because they never stretch. But now the strings that we use in M3, so most of them it involves elastic strings and springs. Okay, so the tension produced when an elastic string or spring is stretched is proportional to the extension. Okay, so this is something that you need to know. The tension that is produced now, when you're pulling the string. Okay, when you pull the elastic string, so if this is the spring, let's say this is the spring. So when you pull it, you create a tension, right? So when you pull it, the moment you pull the string, you can feel the spring. If you release it, it goes backwards, right? Because there's a force produced in the spring or the string when you stretch it. Okay, so this is proportional to the extension. What does that mean? Now the tension produced is proportional to the extension. What does it mean? It means the more you pull, the more tension that you create, isn't it? Because you do realize that when you take a elastic spring, the more you stretch, you can feel the higher the tension on you, right? Okay, so that's why they have given you tension is proportional to what? The extension. Okay, extension is the amount that you stretch. And then what they do is we remove the proportional mark by putting a constant. So tension equals kx, and they say the constant k depends on the unstretched length of the string L and the modulus of elasticity of the spring or spring. Okay, basically what they've done here is they have found here, so we don't need to go into the explanation of how this is found. In M3, all you need to know is this k value is found as lambda over L, where lambda is defined as the modulus of elasticity of the spring. So modulus of elasticity of the spring, it is something that is unique to that spring and it is a constant. It's a constant value for that particular spring or the string. Okay, end of the day, we create the equation tension equals lambda x over L, and this is the main equation that we will be using in this chapter. Okay, in this chapter and in chapter 3, we will mainly be working with this particular equation, tension equals lambda x over L. So everywhere in the M3 book, not only in chapter 2, but also in chapter 3, and also in some places in chapter 4, you will find elastic strings. Whenever you are working with elastic strings, you must use the tension produced in the elastic string is found by lambda x over L, and we'll write down what each person means. Lambda is the modulus of elasticity. Write down lambda is the modulus of elasticity of the string or the spring. X is the extension. X is the extension of the string. L is the natural length. L is the natural length of the spring or the string. Okay, so now remember, extension means the amount that you are pulling or pushing beyond its natural length. Okay, so this particular relationship is what we call as Hooke's law. Okay, so we'll go to the applications of Hooke's law now in exercise 2A, question number 1. So they say one end of a light elastic string is attached to a fixed point A. Okay, so what is it? One end of a light elastic string is fixed to a point A. A force of 4 Newton is applied to the other end of the string so as to stretch it. What are we doing? We are applying a force to the other end of the string and we stretch this. The natural length of the string is 3 meters and the modulus of elasticity is lambda. Find the total length of the string when lambda is 30. Okay. So first, shall we draw a small diagram to visually understand what's going on? Okay, first thing is we have a string. Now you could draw this string either vertically or horizontally. I'll draw it like horizontally, vertically. You could draw it in either direction. Okay, so this is the string and the natural length of the string is 3 meters. So natural length is how it is when it is normally there. Naturally, it is 3 meters in length. Okay, what are we doing now? We apply a force of 4 newtons to the end of the string. So when you apply a force of 4 newtons, what do you expect to happen? What happens? Obviously, the string will stretch. Okay, it's an elastic string, it will stretch. So they say, the question is when you apply this force of 4 Newton, they want you to find the total length of the string. That's what they want you to find. Okay. So I'm going to apply the 4 Newton force and automatically the string will stretch. So natural length is the 3 meters. And then this remaining distance that it has gone. So this is what we call as x, which means what? X is the extension. And why is it down over here at this point? Because of the force that we apply, the force of 4 Newton that we apply to this end. So because of the 4 Newton force, the string is stretched. So the stretched amount is x. The natural length 3, in addition to that natural length, it has the string is stretched an extra distance of x. So with this force that you are pulling, so what is the string giving here? What input does the string give here? When you pull down with the force of 4 newtons, the string is definitely what? Producing a tension. There's a tension producing the string opposing this, right? Because the moment you pull an elastic string, it gives a tension because it wants what? The elastic string wants to go back to its natural length. Okay, it wants to go to the natural length. So there is a tension acting upward to opposing the force. Okay, so then since you're holding it like this, and it's in this case, what do we say here? We can say that this is in equilibrium because you hold it in this manner. So this is in equilibrium, which means what? What can we say about the tension value? We can say that the tension is equal to 4 newtons. Because this is in equilibrium, I mean, you hold with the 4 newtons, so the tension is applied in according to that according to this particular force. So tension here will be equal to 4 newton. And what do we know about tension in these kinds of string? Tension is equal to lambda x over L. Always tension in M3 we use in elastic strings. Tension is equal to lambda x over L is equals to 4 newtons. So what is lambda? Lambda is in part A, they've told us lambda is 30. So input for part A, lambda is 30. Extension, do we know it? X value is unknown. Natural length, do we know it? Natural length is 3 equals to 4. Can't you make x a subject? You can, right? So x equals 4 into 3 divided by 30. Can I know the x value? The extension? 12 over 30, which simplifies as 2 over 5. 12 over 30 is 2 over 5 when you simplify. So now the question is what? Find the question says to find the total length of the string. So what's the total length? The total length of the string is, if you look at it, is it only the natural length or is it only the extension? What is the total length of the string? The total length of the string is this natural length plus the extension. So total length of string is natural length plus the extension. So natural length is 3, extension is 2 over 5. How much is it? 17 over 5 meters. 17 over 5 meters. Is this clear? So now then we can do part B and part C in a similar manner. So for part B and part C, though the lambda value changes, you don't need to change the diagram, right? Because the x value will definitely change with respect to lambda. The diagram stays the same because in all these questions, the force value doesn't change, right? For all these ABC parts, the force is 4 newtons, which means is the tension changing? No. So even for part B, your tension value is still what? 4 newtons. So tension is lambda x over L equals 4. So now for part B, the lambda value is 12. X is unknown. Natural length is still 3. The natural length doesn't change. The natural length doesn't change, right? Equals to 4. So then you can now again get the answer for x. So x equals 4 into 3 divided by 12. What's the answer for x? X equals 1. So here in this case, the extension is 1. So total length of string, can you understand what I just did here? Total length of string is L plus X. Natural length doesn't change. That's 3 meters. X is 1 meter. Total length of string is 4 meters. Is this clear? Is this clear? Okay, so we'll move to question number 3 now. An elastic spring of modulus of elasticity 20 Newton has one end fixed. When a particle of mass 1 kilogram is attached to the other end and hangs at rest, the total length of the spring is 1.4. So can you see what they're saying here? Now here we are not applying a force, but rather we are attaching an object. So it's the same as applying a force because the weight of the particle will act as the force now. It's the weight of the particle that becomes the force. So they say, I think you can see here the lambda value is given. So the force is given. The force is the weight of the object. And then the total length of the spring is also given. But I think you can see they haven't given you the natural length of the spring, right? Okay, so they say here the particle of mass 1 kilogram is removed and replaced by a particle of mass 0.8 kilogram. Find the new length of the spring. Okay, so basically what you have to do here is first you have to consider the scenario under the mass 1 kilogram case. So when the mass is 1 kilogram, how do we work with it? So we'll draw a quick diagram. So this is the spring. It has a natural length is unknown. So while the natural length is unknown, so for this spring, we attach an object of mass 1 kilogram, which means the weight is 1g, right? 1 kilogram weight is 1g. And then, you know, when you give the weight 1g, automatically there is a, obviously when you stretch the spring beyond its natural length, we create a tension in the spring. Okay, so wait, let me mark, this is the natural length. And the length which the string is stretched beyond its natural length is called its extension. X is called the extension. Okay, so I have to, first let's find the value of L here. So what do we know here? We know that the tension is what? Is equal to, the tension is definitely equal to this weight, 1g. So you can write tension is equal to the weight. And what do we always use for tension in elastic strings? Tension is lambda x over L equals to 1g. Lambda value is given to us. Lambda value is 20. Do we know the x or the L value? You can see in the question, they haven't given you the natural length. Neither have they given you the extension, but they have given you something else. What is it? The total length of the spring is 1.4, which means they have given you this full length. This full length is 1.4. So then what we can do here is let's replace x or either L with by using the equation. Like basically I can make a small equation here. L plus x is 1.4, right? Can you see? Natural length plus extension is equal to 1.4. So what is the, so shall we replace the x value here then? So I could use x as what? X is 1.4 minus L. X is 1.4 minus L. So I'll replace here x as 1.4 minus L over L. For L, don't go to replace the L. Okay, because why am I doing this? I want to make my equation with one variable. Okay, don't go to replace L with 1.4 minus x. That defeats the purpose. I want to have the equation with one variable so I can make it the subject equals to 1g. So now you have an equation where there is only one unknown. Okay, so 20 into 1.4 minus L equals to 1 GL, or basically GL. So open the bracket, make L the subject. 20 into 1.4 is how much? 20 into 1.4 is 28. Minus 20 into L is 20L equals GL. Take all the L terms to one side. So 28 equals GL plus 20L. Taking L out, what do we get here? G plus 20. So I get L equals to 28 over G plus 20. Can I know how much L is? Do we get an exact figure or how much? 9.8. You will use G as 9.8 in mechanics in M1, M2, M3. 9.8. So 28 over 9.8 plus 20 is 140 over 149. Now the thing is this, in the exam, actually in your M1, M2 and M3 papers, you do realize they have told you a specific, very specific requirement that whenever you use G as 9.8, the final answer must be given to 2SF or 3SF. You could go until 3SF, but whenever you, now you can see I have used G as 9.8. So you have to go for the answer with 2SF or 3SF. Okay, now is this the final answer, by the way? Is this the final answer? No. So for, because it's the middle answer, I will leave it as it is. But my final answer must be given to 2SF or 3SF. Okay, you cannot, even if you get a good answer with a fraction, you cannot leave it as a fraction. You cannot leave it as a fraction when you use G as 9.8. Okay, so unless they ask you to give the answer in terms of G, the answer is in terms of G, then it's an exact answer. But over here, I think I can't leave the answer in terms of G because I have to add this G plus 20. So I will have to go for the decimal. Okay, so I got the L value. So now when I have the L value, I can go for the next part. What's the next part? They ask me the mass of 1 kilogram is removed and replaced by a particle of mass 0.8 kilograms. So what is the difference now? The same string, the natural length doesn't change, right? But now you have a particle of mass 0.8 kilograms means what? The weight acting here is now different. So weight is 0.8 G now. So tension will also differ, isn't it? Tension will also now differ because tension is now equal to 0.8 G. So they are asking you to find what? They are asking you to find the new length of the spring. The new length means the total length of this. They're asking you to find the new total length of the spring. So the extension is unknown. I will use the extension as X. So again, what do we do? Again, we'll use the same equation. Tension equals to what? The tension is now equal to, in this case, when we replace the 1 kilogram particle with the 0.8 kilogram particle, tension is equal to 0.8 G. Tension is lambda x over L equals to 0.8 G. Are you with me? Lambda value, does it change? Unless you don't change the spring here. So the lambda value will stay the same. Okay, your lambda value changes when the spring changes. So lambda value is, how much was it? 20. Do we know the extension? We do not know the extension. What about the natural length? The natural length we know because we are using the same spring. The natural length that I found here, 140 over 149, can be used. Okay, natural length of the spring doesn't change. So natural length of the spring is 140 over 149 equals 0.8 G. And now what? It's a matter of making X the subject. So 20X equals 0.8 G into 140 over 149. And then the 20 can come to the other side as a division. So definitely we'll go for decimal answers here because I will be using G as 9.8 again. So you can see here it's 20 comes down with the 149. Okay, so type everything in the cal. Can I know the answer for X? Like give it for a few extra decimals at this point. What is the answer here? 1,372 divided by 3,725. Okay, so actually we'll go for the decimal. Make it decimal because we have to go for the decimal. How much is the decimal figure? 0.3683. Okay, so then we are asking us to find the total length of the string, right? So total length of string or the spring, right? Over here, I think it's a spring question. Or is it a string? The total length of spring, right? Okay, so it's a spring. It's equal to the natural length plus the extension. Natural length was 140 over 149. Okay, since I'm using that, we'll go with the X also with the exact figure then. But definitely final answer must be kept to 3SF. How much is it when you add? 1.31. Definitely keep it to 3SF or 2SF. You will not keep extra significance and you will not keep the answer as a fraction. Okay. Yeah, actually, there is a question saying that we have used X twice because in the first sum with the 1 kilogram particle also extension I used X, and even for the 0.8 kilogram particle I use extension as X. So you could change it and say this extension is X1 and this extension is X2, or maybe give two different letters for the extension. I think that would be better, right? Because it's, do we have the same extension for two different weights of the string? Definitely no. So here the extension should clearly be different. So X2. Okay, so extension should clearly be different. Natural length plus X2 is, natural length doesn't change. Regardless, we change the weight doesn't mean the natural length changes. So only the extension changes with respect to the weight. Okay.